One more example in 12.1. It's example 8. It's got an A and a B. And it says, find the derivative of the following curves, interpret the result, and determine the points, if any, at which the curve has a horizontal or vertical tangent line. Okay, so in reading in the textbook, you will notice that taking a derivative of parametric equations is not that difficult. The derivative is going to be dy over dx is going to be the derivative of the y equation in terms of t over the derivative of the x equation in terms of t. So you take the individual derivatives and put them on top of each other, y over x. So for this problem, the derivative of 2 square root of t would be equal to 2 and then 1/2 t to the negative 1/2 over the derivative of t is just 1. So this turns into 1 over the square root of t. Now we found the derivatives. That answers part of it. Then it wants to know where it has horizontal and vertical tangents. What you need to look at when you're doing for a horizontal tangent, that means that this needs to equal to 0. Well, this will never equal 0. Basically what you need to do is look at for the horizontal, you want to know when dy over dt equals 0, because that would give you a 0 in the numerator, which would make the derivative 0. But if you're talking vertical are places where it's undefined, which that only happens when the denominator, dx over dt, is equal to 0. So there are no horizontals in this case. Whoops. T-E-S. Pretend I spelled that right. Oh, it's not asymptotes. That would help. No horizontal tangent lines. Because since there is no slope of 0, there can't be a horizontal tangent. So now in the verticals, when will this happen? It will happen when the vertical tangent happens when the denominator is 0, and that happens when t is 0. So vertical is going to happen when t is 0. If t is 0, the x would be 0, and so would the y. So it's going to happen at the point 0, 0. If you took this a little further, you could eliminate the parameter by saying, well, since x equals t, then y would have to equal 2 square root of x, which squaring both sides turns into x equals y squared over 4, which is the top half of a sideways parabola. So it's going to graph like this, and then you do see that, yes, there would be a horizontal tangent right there. But you could find any tangent you wanted to. If I picked the spot and said t equals 1, I could put it in there, and the slope, according to my derivative up there, is 1. So that slope right there would be 1. And I could find the slope anywhere I wanted to. They had another example. They went out to t is 4, and then the slope would be 1/2. M equals 1/2. Over here, m equaled 1. And so you could find derivatives anywhere you wanted to. At 1, the point is actually 1, 2. Here, when t is 4, the point would be 4, 4, and so on. And so for 0, the one we started with, when t is 0, that is the point 0, 0, and that is when, right here, the slope would be 0. I mean undefined. Let's write it better. Slope is undefined, or I could write slope is vertical. Okay, part B. Part B has x equals 4 the cosine of t, y equals 16 sine of t. We are between 0 and 2 pi. So let's go with our derivatives. X prime is going to be negative 4 sine of t. Y prime is going to be 16 cosine of t. So dy over dx is going to be 16 cosine of t, or negative 4 sine of t, which turns into negative 4 cotangent of t. So the question is vertical and horizontal tangents. When t is 0 and t is pi, the cotangent is undefined. So I would have vertical tangents at t equals 0 and t equals pi. Those points, if I go back and plug them back in, t equals 0 is going to give me, I'm going to get 4 comma 0, and I'm going to get negative 4 comma 0 if I plug them back in. And now when is the cotangent actually equal to 0 for the horizontal? Well, cotangent equals 0 at t equals pi over 2 and 3 pi over 2. If I plug those back in, pi over 2, that's going to give me 0 comma pi over 2. Sine of pi over 2 is 1/16. And then 3 pi over 2 is going to give me 0 comma negative 16. And we could go on and on from there to graph it. If you actually graphed this function, just as a side note here in case you're not looking in your book, it goes up to 1, 2, 3, let's get this 16, negative 16, and counting by negative 4s, 4, negative 4. I'm not drawing it in the order that it came up. I'm going to put the arrows on in a second because I just can't seem to draw it that way. It's this little skinny looking guy, kind of looks like an ellipse. Actually, it is an ellipse. And if I was graphing this, it actually rolls in this direction. This is definitely not rounded like it should be. Shame on me. And so on. And I could see that I've got a horizontal a vertical right here, and a vertical right here, and I've got a horizontal down here at negative 16, and a horizontal at positive 16. They probably all drew at the same time. Here are my horizontals. Right there's a horizontal, right there's a horizontal. And then my verticals are happening right there and right there. And I could find other points too if I wanted to. This concludes 12.1, parametric equations.